All right. Again, my name is Kyler Nunery. I split my time between three things these days. Number one is I'm an entrepreneur in residence for Purdue University, and I focus on advising startup companies that are coming out of the university. The second thing I spend my time on is I work with my sister, who started a business several years ago called MyCOI that tracks insurance certificates. And the third thing I spend time on is a startup of my own that is tracking classified vehicles on interstates. And why I bring that up is because all three of these have some sort of AI touch point for me. So the Purdue University thing, one of the companies I'm coaching is building neural networks to solve a problem. So it's basically like Nielsen ratings plus Shazam, right? So an application that can monitor what people are watching and hearing using neural networks to do that. For the certificates of insurance company, I'm using neural networks to classify insurance documents to help automate more of that process. And the last use case is to classify vehicles that are driving on interstates based on video data. So differentiating a semi-truck from an SUV, from a truck, from a motorcycle. But really, I'm not a data scientist. I'm more of an entrepreneur. And so my mindset, my perspective on this is really, how can we spot opportunity? Aaron Levy had a great quote that said, to spot opportunity for a business, look for disrupting technology that creates a gap between how things have been done and how they can be done. And I feel like that simple statement has paid off for me in some of the pursuits that I'm working on right now. So the vehicle classification company that I'm working on, the state of Virginia currently spends $3 million a year to collect one metric that they have to submit to the federal government. And one of the ways that they do that is by hiring consultants who go out to the roads and with a clipboard and literally mark off how many SUVs have driven by. So this is a clear case where you can say, we've got this disruptive technology, how can we apply that? And really, that's my hope out of this talk. So this is sort of like a show and tell, a little bit of entertainment, but my hope out of this is that all the while you're thinking of use cases that you could potentially apply this technology to. So first, let's triangulate ourselves in the world of neural networks. When I was getting started on this, so you've got the big ball, which is all of artificial intelligence. Within artificial intelligence is machine learning. Within machine learning is deep learning. Within that are neural networks. And really the core of the neural networks that are out there today are these. These are the ones that are most used. So the ones I'm going to briefly touch on today are CNNs, which is convolutional neural networks, and GANs, which are generative adversarial networks. The other two not covered here are recurrent neural networks, and currently the most popular recurrent neural networks are LSTMs, which were mentioned earlier, and GRUs. And then Q-learning is another type of learning which shares some similarities with evolutionary algorithms that were covered earlier as well. But this sort of locates us in the universe of artificial intelligence. So the Hello World example for machine learning, if you haven't seen it already, is the MNIST data set. And so these are handwritten numbers that we try and teach a computer to recognize these handwritten numbers. So what does that look like really is an image of this number 8 is really pixels, and each pixel's a numeric value. So this number 8 translates into a bunch of zeros and then a bunch of grayscale numbers. The image is a 28 by 28 pixel image, so that is 784 inputs. So to solve this problem, you would build a neural network that has 784 inputs, and the output of that network will be 10 neurons, and that's because the first neuron represents the score of the 0, the second neuron is the score of the 1, etc. So really, if you have a binary classification, you could get away with one output neuron. In this case, we're classifying between 10 things. In my vehicle case, we've got 13 different vehicle types, so we've got 13 outputs. Before I go there, so I want to give an intuitive feel. For the non-data scientists in the room, I want to give sort of an intuitive feel of what's happening in a neural network when you're training it. So you take a labeled data set like this number 8. We know that that's a number 8, so we pass in all of those inputs. All of the connections between the inputs and the outputs are random values. So between -1 and +1. So if it's a -1, whatever value it sees, it will hold back. It will actually reverse. If it's a +1, it will sort of push forward the number that it sees in its input. So the way I think of this is it's really like wearing all of these connections between neurons are really grooves or peaks that the system is learning on its own. So a convolutional neural network, if you're curious about convolutional neural networks, like what are they exactly? I hear people talking about them. There's a fantastic blog out there by a gentleman named Brandon Rohrer, R-O-H-R-E-R, which does a fantastic job of describing this. But the point I want to communicate here is, here we have another example where we're trying to classify, is the image an X or an O? In a convolutional neural network, a high-level way of saying this is that you take these things in the middle are the filters. And those filters, you slide across the image, and you do a multiplication across all of the pixels and your filter values. That's all a convolutional network really is just like a neural network, but instead of connecting every pixel in this X to every output, instead you have this sort of middle layer that has these filters on it. So you can see that for an X, if I convolve it with a filter that has ones on the diagonal axes, here's the result I get. So you can see how this filter gains sensitivity to features that are on the diagonal. Likewise, this filter, which looks more like an X, really activates in the center of this image, because that makes sense, right? The X matches this little X down here. And likewise on the right diagonal as well. So with that, if you look at, you can take these filters, and just like I had here, you can consider this like an image, right? All these values could be considered an image. Well, if you look at those, and you look at the MNIST data set, those lower level filters start to learn attributes of the data. So in this case, this is a visualization of the lower level of an MNIST data set, and it starts picking up almost like stroke marks of your numbers. Applied to a different domain, this is a data set trained on human faces. So the lower levels start picking up edges and contours that may show up in the data set. The higher level, the middle layers, because this is a deep neural network, right? The middle layers start picking up higher level features like noses, ears, mouths, etc. Top level really has that higher level abstraction of content. And what's amazing is that the networks will learn all of this themselves without you saying, I want a feature that is a diagonal. The system will initialize this with random values and will eventually learn these filter values. So what's happening here? What is really going on, the power of this is that it's automated feature engineering. So if you're trying to build a system that can recognize a human face, you may use OpenCV and do edge detection. You may try and do some calculations looking for the ears, and an ear is something that's taller than it is wide. You may hard code a feature like that into your system. But what this is doing is it's really learning those things for you, and it's training itself. And the important point is it's encoding more advanced features than you could code yourself. Imagine writing a neural network by hand that would distinguish these, right? That's a hard problem. But for neural networks, it's easy. An even harder problem. Anyone know who the person on the left is? Drummer for Red Hot Chili Peppers. So this is Will Smith, of course, and Chad Smith. And, oh, I'm sorry, thank you, Will Ferrell. That's what happens when you're live. All right. So I'll show you just with a neural network trained on this. I'll fire up a simple Python file, and if all goes well, if the demo gods are with us today, this will, yeah. So in real time, the neural network is picking up my face and labeling it, and if I hold up Will and Chad, Will Ferrell, which way? Other way. Chad Smith. So the neural network is actually able, it has encoded in it features. Hey, great, you can clap, that's fantastic. I didn't write it, but that's okay. We'll overlook that. So why now? This is something that was covered previously, but really, For the neural network to pick up these features, you have to have a lot of data. Well, that's one thing that we're swimming in as of late. And then GPUs. So NVIDIA, who built gaming cards, serendipitously ended up in a very good spot for training neural networks. And that gives us our AI of today. But this also would not have happened if it were not for Jan LeCun. So Jan committed career suicide in academia by pursuing neural networks since probably the mid-90s, I think. And because he stuck with it, that's why we're getting benefits today. And this is actually a video from, oops, was a video. All right, well, I won't even show the video, but this, you can tell by the computer and the keyboard, right? This is from 1993, and this is that MNIST data set, and the camera pans to the right, and there's a young Jan LeCun sitting at the keyboard. Let me show you, so from here on out, that's sort of done with the theory for the most part. I'm going to show some demonstrations of what's happening here. Tech support? Anyone? Connected, secured. Someone make a Windows joke now. All right. Okay, so this is an example. This is an app built by Google, and it says draw a swan. And so I'm going to quickly.
I see bird, or bush, or shoe. I see shrimp, or toothpaste, or clarinet, or garden hose. I see frog.
I don't know what else to do there.
Or dragon.
Dragon.
Or tiger.
Okay. Yeah, me too. So I'm not quite good enough with the mouse to draw that, but you can see like that's not hard-coded, right? Like it's analyzing it as I draw it. Oops. All right, so all of these things that we've done so far fall into something called classification, where you just pass it an image and it tells you it's a cat. But there are a couple different shades of this. The next one is classification and localization, so draw a bounding box around the object that you've detected. The next level up from that is object detection, so given a whole scene, draw bounding boxes around all the different objects that you recognize. And then really the state-of-the-art contests are focused on instance segmentation, where you actually draw the outline around the image. So here are a couple examples of that. This is an algorithm called Yolo, which stands for You Only Look Once. And it's using, this is in real time, by the way. So the algorithm is actually doing a feed-forward inference on the neural network as quickly as you're seeing it here, which is just incredible. So Yolo is used in lots of self-driving car examples. One second. And nope, thank you. And likewise, this is another demonstration of some autonomous vehicle. This is doing the segmentation. So you see the road is purple, the cars are dark blue, the buildings are red. So this is really what your car is going to see, or what your Tesla sees today, if you're using it. Some other party tricks that this technology is doing is something called style transfer. So you pass these two input images, one of a photograph and another one of an artist, and a neural network will actually merge those two images and create a new image out of it. Here's another particularly good example. You can actually do this yourself on deepart.io and download the pictures. So how is it doing this, right? So back to those convolutional neural network filter windows. So this is a network that has n number of layers, but the lower layers on it naturally pick up the edges. So without anyone telling it to pick up the edges, it naturally figures out the edges because those are the lowest level. Above that are the textures, above that are the patterns, and then at the highest level are the objects. So all you have to do is take your loss function that you would do with a typical neural network, which is calculated based on how different, like if it's a number 8, but it tells us it's a 60% probability of a 6. From that, you calculate a loss function, and that loss function drives the learning. So in this case, your loss function, instead of being based on the output, is a combination of the style loss plus the content loss, and then the total loss. And it turns out when you tweak that loss function, that's all that's needed for a neural network to produce an image like this. This is the state of the art in this field. Is on the left is a photograph, on the right is a painting. You want to do style transfer to those things. If you use deepart.io, it won't turn out so well. It will apply clouds in random places and mountains in different places, but it doesn't really understand that there's a connection between the clouds and the mountains and the mountains. A technique called deep image analogy has actually solved that, and so it can generate this result. But we're not limited to just pictures, right? We can use video. So this is an experiment where they did style transfer on every image within that video, but then they tweaked their loss function to have a temporal consistency, and now you see this. So you want to see that again? All right. Actually, I'll fast forward to some of the cool examples that they did with Disney if I can. All right, so this is without a temporal loss component, and then this one is with a temporal, and you can see it does some pretty amazing things. This video, you can look on the deck, goes on to show some scenes from other Disney movies, which are just amazing. Like, Disney has to be going bonkers over this stuff. All right. No, we're done with you. I'm glad someone's old enough to get that joke. All right. So where is all this going, right? Like, where is all this headed? This is sort of the bleeding edge. It's something called a Generative Adversarial Network, or GAN. And this was a brilliant concept that what it does is it takes, right, it's two neural networks. The first one is trained on a specific domain, and you pass it noise. So just random noise being passed into it. And as it follows all of those peaks and valleys through the network, it will generate an output. And in this case, if you're wanting an image to be the output, all you have to do is have 784 nodes on your output, and it'll generate another 28 by 28 image, right? So you can basically leverage a trained network to not just tell you what something is, but to generate something new. And this has been a watershed for machine learning. The second network takes what's generated by the first network, and it's called the discriminator. So its job is to say, that's real or that's fake. So you pass it real examples and fake examples, and over time, both of them learn together, and you reach an equilibrium where the generator becomes really good at generating things that look real to us. This is a brief video that shows some time lapses of a GAN being trained. So why is it doing that? There we go. So you'll see at the beginning, it's very rough, like hardly even features at all. But within several epochs, you get this network starting to generate realistic looking things. If I let it run for a minute, you'd see the finely tuned things that it comes to at the end. So I want to show an example of noise to image, because this was kind of hard for me to wrap my mind around when I first came to it, but this is a good demonstration site of that. So this is a network that's been trained on Asian faces, and on the bottom is the input of the network, and the top is the output. So you'll see, and I can draw on it, right? So I can draw, just change the randomness nature of it, and I can say generate a new. And it's close to the previous face, but it's not exact, right? It's changing ever so slightly because it's following a different path through those peaks and valleys. And we'll just see, just for grins, like what is the furthest, if we did an all black pixel image, okay, it's a woman there. What if we did the opposite and we passed a bunch of white pixels to it? And we'll see. Okay, good enough. Generate that. It's a male face image. So all of these different faces are encoded in the grooves of this neural network. Credit for GANs goes to Ian Goodfellow, who was mentioned earlier. Here's some really crazy examples of this. What you see here, so I'm going to show you a series of images. The first image I show you is the input, and the second set of images are the output. So in this, and this is something that you can even do online. There's an online demo of this. This is your palette, and or this is your canvas on the right, and on the left is your palette. So you can click on the window in the palette and draw a box on this image and construct something, right, that's going to look like a building. And this is what it generates for you. I think that's amazing, right? Like, think about what this is going to do to architecture and design, right? When someone can just draw a sketch of a building that they want to see, and the network, because of all the data it's been trained on, is able to generate something, and they go, yeah, I really like that, or no, that sucks. Like, that really is a groundbreaking change. Here's a similar representation where the computer will generate a photograph of a mountain when the user simply draws a black triangle like that, and then he wants to put some clouds, so he draws blue lines, and then he wants some snow. And you can see on the right-hand side, the image is evolving according to those sort of high-level instructions. Something similar with faces. So this is in real time. This is someone like choosing a color out of paint and then clicking on the photo and changing the hair color from blonde to brunette to longer hair, changing the color of the teeth, etc. What you can also do with these is learn not just how to generate things, but you can basically create sort of what I think as an amateur data scientist is like an autoencoder. So this is learning relationships between apples and oranges. You pass it just tons of images that are labeled as apple and orange. And this is the input, our apple, 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 orange. And then it can generate an image which has matching qualities to the apples, but they're oranges. Again, not limited to pictures. A horse that becomes a zebra because it's been trained on lots of images of horses and zebras. So it still looks a little bit trippy, but this is like V1, right? All right. No. Yeah. Okay. But, of course, it doesn't always behave, right? You're seeing all the best examples of this. So as Vladimir Putin was quoted as saying, the person who owns AI will own the world. So this is particularly appropriate. I like to call it Putin. This is a system that has learned cross-domain relationships between purses and shoes. So not finding styles of purses that match styles of shoes, just lots of images of purses and shoes. You pass it an input of a purse, and it will generate a shoe that does not exist, which matches the style characteristics of the purse. Summer and winter photographs. This is the input, and this is the output. Male and female faces. This is the input of all male faces. This is the output. These people don't exist. Ages, right? We've got lots of pictures of human faces, and we know their age, so why not throw that into a GAN and see what comes out? These are photos of some teenagers, and now you can age them over decades. This has already been incorporated into a business app called FaceApp. I think it's maybe somewhere in Eastern Europe, a company that did this. You pass it an input image, and you make it smile. You make her smile. You pass it an input, you make them older, younger, change their gender. This is already out there. I find this one particularly interesting. So anyone who's done like Blender or AutoCAD, who's designed 3D models, from one single image, this is generating a texturized OBJ, like full 3D model. So this is, in this case, a young Donald Trump from just one photo. It's generating this three-dimensional image. And I know I'm running out of time, but let me show you. Here's my photo. This is a website you can get to. Now watch. Right? In real time, from one photo, with a big forehead. All right. So as you're thinking about this, think about, everything we've seen so far are really like pixel-based, but it doesn't have to be constrained to that. Like pixels become numbers in an array, but other domains can be covered as well. Sound can become numbers in an array. Think Shazam. Words becoming numbers in an array. Think sentiment analysis. Activity, fraud detection. All right, I'm going to try this.
Hey, Doc, have you heard about this new technology? Are you speaking about this new algorithm to copy voices? Yes, it is developed by a startup called Lyrebird. This is huge. They can make us say anything now, really anything. The good news is they will offer the technology to anyone. This is huge. How does the technology work?
Hey guys, I think that they use deep learning and artificial neural networks.
Hillary is right, and I can tell you that their team is great. I wish them good luck. I'm sure they will do a good job.
All right, combine that thought with this one. And full disclosure on this one is not done with pure neural networks. It's got some pre-processing steps, but you'll see where I'm going on this. So what you're going to see here is video of a loop of Donald Trump in the lower left-hand side, and on the upper left-hand side is a video from a webcam. And you'll see Donald's mouth on the lower left. You can't see it, but it's closed, right? Now watch and see if you can see what's going on here. Right? So we've got you add those two things together and we've got some serious fake news coming our way soon, so. All right, one other example, it can learn cross-domain relationships. So you train a GAN on text and photos that text represents, and now it can generate photos from text. So the input says, this bird has a yellow belly and tarsus, gray back, wings, and brown throat. It generates an image of a bird that meets those criteria, right? And what's actually happening here is the top image is what's initially generated, and then it's passed through another discriminator that tries to augment the image to make it look more realistic with a discriminator. So all of these things that I've shown you, this is a list, and this is for anyone who's got the slide deck. These are all links into the archive, arxiv.org academic papers that highlight each of these things. But if you notice, all of the dates of these are all within the last 10 months, right? So imagine what life is going to look like in 5 years, in 10 years at this rate. That's a mind blow for me. All right, the other point I want to make, and I'm going to finish real soon, is to get into this, these tools are very accessible, right? So TensorFlow and Keras. Keras is an abstraction layer that sits on top of TensorFlow. If you're a researcher, you probably want to start with TensorFlow first. If you're a practitioner or someone who wants to use these tools, it's probably going to be easier to use Keras. But Keras supports multiple, not just TensorFlow, but Theano and CNTK and a couple of others. So I'm seeing a real convergence point with Keras in the design of this. Here are some of the many use cases, right? Like this is a partial list, but some really amazing things that you can do with this technology with business application. So think about AI in a video game. That the thing controlling the monster that's fighting against you is being governed by 1,000+ hand-coded rules that were written by someone. Imagine if you train that monster to move based on neural networks, they're actually going to outperform any human very quickly, and that's what we're seeing. Or imagine another example where you have an HR system, and you pass that HR system all of the credentials or maybe the resumes of all of your employees, and then you rank all those employees 1 through 10. You train that on a neural network. Now you've got a system that when you are interviewing candidates, you can plug in their resume, plug in their credentials, and see that an 8.5 pops out on the other side, right? Those are just some of the potential applications. So if anyone is interested in this and following along, I've started meeting with a group at Purdue on Friday afternoons, and we're calling it Machine Learning Study Hall. It's really just a time for, it's a small group. There's actually one guy in the group who's a professor and studied under Jan LeCun, so some really knowledgeable people. If you're interested in participating in this, please drop me an email. And that is all I have. Thank you very much.